Now, let us see what happens for multi-component systems. For multi-component systems, if we take it up, just the same equation with some more terms. Again, I repeat, we are going to deal with only PV type of work, and I will be doing the entire derivation considering internal energy, keeping in mind that the same derivation can be applied for other systems as well. So, in this particular case, what did I write down initially? This was equal to del U del S at constant V dV for closed systems, del U del V at constant S, sorry, this was ds, this was dv. Now, if I have more than one components, then what do? I keep this is equals to n I not equal to j. This is n I not equal, sorry, n j not equal to I, n j not equal to I, where I vary the number of moles of the nth component. So, therefore, this is going to be del u, say del n1 at constant SV n2 to the final component nm or whatever number, or say nc, where nc is the total number of components. Okay. So, therefore, it goes on continuously into dn1 plus del u del n2 dn2, again this is at constant SV n1 n3 till n, I will make the number of components n, plus so on, we can keep on writing. So, therefore, this can be summarized and it can be written down as this is equal to del u del S constant n j not equal to I ds plus del u del V constant S n j not equal to I dv plus summation of I equals to 1 to n, where n is the total number of components, del u del n I constant S v n j not equal to I. I am sorry, in this particular case I am extremely sorry, it should have been total n. I am very sorry for this mistake, it should have been total n, right. So, therefore, this is the final equation which we are going to get for multi-component systems, and in this particular equation we find that each and every variation of u with the mole numbers, each of them they correspond to the chemical potential of that particular component mu2. So, therefore, this can also be written down as del u del S at constant V n ds plus del u del V at constant S n dv plus sigma I equals to 1 to n mu I dn I, right, where each mu I, it corresponds to del u del n I of the ith component, where the number of total number of moles of all other components except the ith component is kept constant. I have written down the equations for the multi-component open systems in each case, you can see, and in each case again it can be proved that the property change due to the change in the number of moles of component I, when the number of moles of all other components are kept constant, is given by mu I dn I in each particular case, where mu I, just like mu for single component systems, in this particular case also we find that it corresponds to the molar internal energy or the molar thermodynamic potential subject to the respective constraints, and in reality it is the molar isobaric isothermal potential when the number of moles of any one component is changed while the number of moles of the other components are kept constant. And in this case also, just like the previous case, we can define the Gibbs-Duhem equation. In fact, the Gibbs-Duhem equation is much more convenient when we are defining it for multi-component systems. In this particular case, the equation becomes SDT minus VdP plus sigma Ni d mu I equals to 0, and at constant T and P, this becomes sigma Ni d mu I equals to 0, and if we divide it by the total number of moles, it becomes sigma Xi d mu I equals to 0. The importance of this equation can be immediately understood if we know the composition of the mixture, and if we know the chemical potential of n minus 1 number of components, we can use this particular equation to find the chemical potential of the nth component. Say for example, for a 2 component system, this just reduces to x1 d mu 1 plus x2 d mu 2 equals to 0 at constant T and P. So, if we know x1, if we know the change of mu 1, then by using this equation we can find out this particular quantity, and there is where the importance of the Gibbs-Duhem equation. This is the Gibbs-Duhem equation for multi-component system, and we will find later that this is very important to test the thermodynamic consistency of the data that we use, because we need to remember that most of these data, they are obtained from experiments. So, therefore, before using them for any particular calculation, it is very important to test that these data are thermodynamically consistent, and this particular equation is usually used to test the thermodynamic consistency of these data. Now, before we go further, it is very important to understand that why is this so very important term, the molar Gibbs-Way energy given a special name, and that too the name is chemical potential. Is it really a potential in the true sense, just like U, H, A and G? Now, in order to understand this, we have to recall the properties of a thermodynamic potential, which I had already discussed when I was discussing, or when I was trying to explain why U, H, A and G are thermodynamic potentials. What are the properties of thermodynamic potentials if we recollect? The properties of thermodynamic potentials are, if you remember, firstly the value has to be independent of the integration path. What does it signify? It signifies that these particular property, or rather these particular potentials, they have to be properties of the system. Definitely chemical potential is a property of the system, we know that. So, in this case we do not have any problems. The other thing which we found out was that all these potentials, they must be in units of energy, right. Here also definitely chemical potential, it is measured in the unit of energy, but that is primarily accidental. Why? Because a chemical potential mu I, it is nothing but equal to del G del N I at constant T P N J not equal to I, and this particular number of moles, it is basically a number. Had I expressed it in terms of concentration, then this would have been an energy concentration instead of an energy unit. So, therefore, since mu I is defined in terms of Ni, so therefore, it has the units of energy, but that is primarily accidental. And what does the third condition of potential imply? It implies that the minima denotes stable equilibrium, which we already know while we were discussing equilibrium under different conditions. What did we find? We found that du Sv was equal to 0, the conditions of equilibrium were, and then dHsp was equal to 0, then dATV was equal to 0, and dGTP was equal to 0, right. So, therefore, we find that for each and every case, the differential quantities are equal to 0. But in the case of chemical potential, if you observe this particular equation and this particular equation, it immediately appears to you, it is not that the d mu is equal to 0, this does not happen. On the contrary, sigma mu I Ni, this is equal to 0. So, therefore, if you observe this, that the summation of chemical potential for any particular reaction or for any particular process equals to 0, then it appears that it would have been better if it would have been called by the name of the force, because we find that this particular characteristic combines with, or rather this particular characteristic, it corresponds to a force quantity. But again then we found out that if we name it by the force, then we find that we have a force which has the unit of energy. That is not something very convenient. And the next thing which we observed was that very frequently we find that for non-equilibrium conditions, the currents, the driving force for currents, they can be identified with the gradient of chemical potential, because very frequently we find that when we are dealing with non-PV type of work, then we are dealing with electrical work, and under that condition the current, it is usually defined as the gradient of potential energy. So therefore, under that condition we find that it is a force being a derivative of a force. That is also not a very comfortable feeling. So therefore, what I mean to say is chemical potential is something very unique which combines some of the characteristics of potential, but it cannot be considered a thermodynamic potential in the true sense. It has some characteristics of a thermodynamic force, but it cannot be considered a thermodynamic force in the true sense. It has the unit of energy, it is an intensive property of this system, but the summation, it corresponds to equilibrium, and its minima does not correspond to a stable equilibrium. So all these things suggest that chemical potential has a unique place of its own, and since it combines a large number of characteristics just because the way it has been defined, so therefore it has got a multifaceted aspect, and since in the absence of any better name, we would like to prefer to follow conventions, and we would like to continue calling it as a potential, but not a thermodynamic potential, but a chemical potential, keeping in mind that it is not a true thermodynamic potential. The next thing again which I would like to say, that what have we done in this particular case? For this particular case, we have found out, or rather we have related each and every thermodynamic potential with the chemical potential term. Now, it would be interesting for us to find out that if we notice that for an isolated system, what is the criteria of equilibrium? For this particular case, it is ds isolated equals to 0, where we know that S is not a thermodynamic potential. So therefore, in this particular case, it will be interesting to find out how this particular term del S del N at constant uv, in what way is it related to the chemical potential. Now, this particular derivation, it's slightly involved, but we can go through it and we can try to appreciate, keeping in mind that although this is not a chemical theory, or it's not a thermodynamic potential, it is often used in order to find out the criteria of equilibrium for an isolated system, and it has got a very interesting relationship with chemical potential, where the relationship is not of this particular form. Let us see this particular relationship before we proceed further. Now, in this particular case, can we not write it down in this particular form? ds equals to, we can write it down as, say, del S del N at capital UV, right. We would like to find how this is related to mu. Now, this particular equation, we can definitely write it down as Ns at constant uv, which is nothing but equal to, just like we have been doing for all cases, del S del N at constant capital uv. Now, I would like to remind you of a very important rule of differentiation, which is given as del z del x at constant m is nothing but del z del x at constant y plus del z del y at constant x into del y del x at constant m. So, if we apply this particular equation here, what do we get? We get del S del N at constant capital U capital V is nothing but del S del N at NV, UV plus del S del U at NV into del V del N at UV. We can write it down in this particular terms. Then this particular term can also be expanded in the similar way. We can again write this term as del S del N at small u small v plus del S del V u n into del V del N u capital V, right. So and then we can substitute this equation there. Once we substitute, what do we get? We get del S del N at capital U capital V. This is nothing but equal to del S del N small u small v plus del S del V small u small n into del V del N u v plus del S del U N V del U del N capital U capital V. We can write it down in this particular way. Now, if you observe this equation, what do you find? The first thing is this particular term del S del N at small u v, this term, this becomes equal to 0. What about this term? Here I would like to remind you that TdS equals to du plus PdV, right. So from there, what is this term equals to? Can you tell me? This term then becomes equal to P by T. What about this particular term? This term becomes equal to 1 by T. So therefore, and we have to keep in mind that capital U is nothing but equal to NU, capital V is equals to NV, and yeah, so therefore from there what do we get? We get del U del N capital U V. This is nothing but equals to del N of U by N capital U V, which is nothing but equals to minus U by N, or in other words, this is equal to minus capital U by N square. Same way we can write it down as del V del N capital V U is nothing but equals to minus V by N. So therefore from there what do we get? Del S del N at capital U V, it is nothing but equals to minus of U plus PV by Tn. From there what do we get? We get that then this becomes equal to and if we substitute this particular term in the first equation that we have, then finally what do we arrive at? We arrive at a condition that del S del N capital U V is nothing but equal to S plus N U minus PVN by Tn. From where what do we get? We get minus of, so we get minus of U plus PV minus Ts by T, which is nothing but equals to minus mu by T. So therefore what do we get? We get that del S del N at capital U V is nothing but equals to minus mu by T. So therefore we were trying to find this relationship. We know now that this is equals to mu by T. So therefore the combined first and second law for open systems with only for only PV work, from combined first and second law and single component system, for all these conditions, what do we get? We get ds is nothing but equals to 1 by t du plus p by t dv minus mu by t dn, or in other words t ds equals to du plus p dv minus mu dn. So, this is the equation which we derived. The derivation was slightly involved with a large number of capital and small case alphabets involved, but by this particular discussion what I wanted to impress upon you is the importance of identifying the total and the molar properties, and I would like you to remember that we are not dealing with mass specific properties at the moment. Same equations will be applicable for mass specific properties as well, and from here what we came to know is when we have to deal with open systems, when the system interacts with the surroundings not only by energy interaction but also by changes in the number of moles or by mass interaction, then we find that we had to introduce a new chemical property which was actually not new. It is basically the molar Gibbs free energy, but we had called it by a new name, the chemical potential. Why did we have to put a new name to it? Because we found out that for single property system it was the molar Gibbs free energy, but moment we are dealing with multi-component systems, we find that this particular property becomes equal to mu I in this particular case, right. So, therefore, just in order to combine both single component and multi-component systems, we had defined, or rather we had defined the molar Gibbs free energy for single component systems as chemical potential, and we keep in mind that for single component systems chemical potential is equal to this particular expression which for a multi-component system it becomes del u del ni sv nj not equals to I, and so on and so forth. And both these terms, they are referred by the same name. It is known as the chemical potential, and we will remember that the chemical potential is not a true thermodynamic potential, but it has a number of characteristics of a thermodynamic potential. So, in the next class we shall be going to deal with open systems. First we are going to deal with single component open systems, and then we are going to extend it for multi component open systems.